Hello, I'm Lixing Lu from the Kunshan University, and this presentation is about the final project of my Math 304 course, the Numerical Analysis and Optimization. And this project is about least squares regression. In the next couple of minutes, I will introduce which problem this project is solving, the methodology, my experimental results, the discussion, and the conclusion. In this project, I was given a couple of data points like the left corner shows. My goal is to plot out the polynomial models that fit the data points the best. The x values are interpreted as x0 to xk. Because I am looking for polynomial models, I extend the x matrix to the size k times n plus 1. What I want to figure out in this project is just the coefficient vector that gives the predicted y hat vector that is closest L2 distance with the actual y vector. Next, I will introduce the methodology part. The solution of least squares regression is not hard to calculate and can be obtained by one-line code in MATLAB. However, directly implementing least squares regression does not guarantee a well-performed model. I trained the model on two different datasets. The small one has 10 points and the large one has 100 points. We can find from the error table that when we set the n value to be 9, although the large dataset error is satisfying, the small dataset model returns really high error, which is vividly displayed in the plot. The red curve that represents a small dataset does not fit well with the actual dataset. In order to improve the performance of small dataset model, I'm introducing L2 norm regularization method in the next couple of slides. So how L2 norm regularization is affecting the model performance? We can see from the loss function that I'm adding in a new parameter lambda to add penalty on the size of coefficient alpha. This avoids that some alphas being too large and the model becomes too sensitive to outliers. Due to the time limit, I'm not explaining how I implemented with the least squares regression. But we can see from the results that the blue curve, which has the regularization method, is far smoother than the original one, the red curve, and fits the data points better. The mean squared error dramatically drops from 4.98 to 0.14, so this method thus works. Now that the L2 norm regularization is improving the performance of small dataset model, does that also work on the large dataset model? We can see from the plot that the two curves are very close and the mean squared error even rises a little bit. So it seems that the regularization method doesn't help on the large dataset. Then we come to how to decide the best regularization weight lambda. Here we just randomly pick 5 different lambda values. You can see from the list, and of course you can just pick other ones. We does not use the mean squared error on the test set to list out 5 mean squared error and decide the best one. We use the cross validation to calculate the average validation error, and the least one gives the best result. We first randomly shuffle the datasets and divide the training dataset into 5 folds. Here we just pick the number 5, and of course other numbers can be picked. We can pick 10, you can pick 8, and that doesn't matter. We just pick one different fold each time as the validation set, the left 4 as the training set. We train on the training set and calculate the error with the validation set, then just repeat the step 3 and step 4 5 times until we just iterate through all the folds. We take the average error of each lambda value, and the least one gives the best performance. The advantages of this cross-validation is that we randomly shuffle the dataset and just validate k times. This is more representative than the original mean squared error, and this method is very commonly used. So finally, I'm sharing my experimental results. My task 1 I get is to train the model on small dataset without L2 regularization method. I scattered the data points and just try different n values. We find that when we set n to be 9, it gives the best training performance, but the worst testing performance. The best testing performance model is when we set n to be 2, but you can see from the plot that the curve is a little far from the actual data points. In task 2, I trained the model on large dataset without L2 norm regularization. So here we can see when we set n to be 9 or n to be 5, the curve are almost very close. And n being 5 gives the best testing performance, and that's the result. In task 3, I just try L2 norm regularization and try different ways to return the mean squared error. You can see that 10 to the power of -6 gives the best testing performance. But when we use the average validation error, we find that when lambda equals 10 to the power of -3, the result is the best. So that's just two different methods. And next, I would like to share some of my thoughts on this project. And some of my conclusions. Firstly, large dataset outperforms a small dataset. We can directly see from the mean squared error. And secondly, L2 norm regularization improves the performance of small dataset model, but does not help improve the large dataset model. Yeah, this is probably because when we use a small dataset model, it has overfitting problem, and the large dataset is sufficient to support those parameters, and the regularization does not improve quite much. And I would like to share some of my thoughts on possible methods to further improve this model. From the first point that large dataset outperforms a small dataset, maybe we can do data augmentation to expand our dataset more and try more parameters to give better results. Also, we can use different regularization weights, like actually the two weights, the 10 to the power of -3 and 10 to the power of -6 are quite close. Maybe we can pick some middle ones, like -4, -5, see if they are giving better results. Last but not least, I would give my sincere acknowledgement to Professor Wang. Thank you for introducing so many practical optimization methods, and many of them I have never heard of before, and I believe that they will be very helpful for my later academic. Thank you so much, and also thank you everyone who ever watched this video. Have a good day. See you.